Okay, so now I want to talk to you today about energy unit conversions. I want to also talk to you about specific heat and specific heat problems, as well as what is calorimetry. So let's start off with the energy unit conversions. This is 1 lowercase calorie is equal to 4.184 joules. The reason why I emphasize that this is a lowercase c is because the capital C for calorie actually represents a dietary calorie. That means that when you are looking at your food packages and you're counting the number of calories that you've eaten, that calorie is actually a capital C. So the capital C is the food calorie that you have. And that 1 capital C food calorie is equal to 1 kilocalorie, which is also equal to 1,000 calories. Okay, so now let's do a problem that has the unit conversion on it. This is what is the equivalent in joules of 126 calories. And remember, this calorie is a capital C, which is a dietary calorie. So this is what you're given, and you need to find the number of joules in it. So start off with what you're given, and you're going to do regular old-fashioned dimensional analysis. So you're going to start off with 126 capital C calories, and that 1 capital C calorie is equal to 1,000 lowercase c calorie. That 1 calorie is equal to 4.184 joules. All the units except for joules cancel out, and you are left with 527,184 joules. Keep in mind that this is 3 significant figures, so your answer is not going to have the last 3 digits on it, so it's just 527,000 joules. Now go ahead and pause the video so that you can do the other problems, and then unpause it to find out what the answers are, or just to check your work. Okay. So hopefully you've done the other work, and you can see right here I've done example number 2 and example number 3. Each time keep in mind the number of significant figures. This is 3 significant figures, and then the last one, example number 3, is also 3 significant figures. So keep in mind with the significant figures, and make sure that you do your calculations correctly on here. Okay. With that, now I want to talk to you about what a calorimeter is and the basis or the theory behind calorimetry. So a calorimeter is a device that's used experimentally to determine the heat associated with a chemical reaction. And the whole purpose of a calorimeter is that it is there for measuring heat. And the way that a calorimeter actually does this is by observing the change in temperature within the system itself. It either absorbs the energy or it actually releases energy. And this energy that we're talking about is usually in the state of heat. So a really good example of a calorimeter are thermos bottles that you use. Yeti these days is huge. And that's definitely something, a calorimeter that you can use. So what happens is that you have here a container, and within this container you have another container. And this is really the purpose of the whole idea behind Yeti. So you come in contact with this outside container, never coming in contact with the inside container where all the heat is. So when you pour a hot liquid in here, it prevents the heat from either leaving the first container or any extra heat or from entering the container also. It actually prevents it. And the way that it does is that there's usually some kind of insulation in here that either absorbs the release or the it either absorbs the heat or it prevents the loss of heat. So it's this material in here that allows heat to remain where your beverage is either hot or your beverage just never gets cold, okay? Or your beverage just remains cold. So either you've got a hot beverage or a cold beverage in here. So that's the basis of a calorimeter. You can put a thermometer in here to measure the temperature. You can put a storing rod in here also to store things around, but it's basically an insulated cup within a cup. So now to talk about this now basically to talk about a calorimeter, there are certain things that you need to know, some concepts here. And one of the first concepts that you really need to know about a calorimeter is the concept of specific heat. So a specific heat is the energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius. I'm going to highlight that for you because that is extremely important for you to know and for you to understand. And I think the biggest idea out of this is that there is an increase in the temperature of 1 gram of a substance by 1 degree Celsius. Okay? And usually the way that this is actually measured is by joules over degrees Celsius times grams. So another way of writing is by writing joules, degrees Celsius, grams, or we can write joules over Kelvin grams. This is not kilograms, but this is Kelvin grams. So keep that in mind. So here's a table, a really small table that you have, quick one, that gives you an idea of the specific heat of all the substances. Realize that the substances, for the most part, are in joules. Joules divided by degrees Celsius times grams. Each one of these, and there are all these different substances around here. You don't have to memorize this because this is a table that is always going to be available to you. A table full of the specific heats of different substances like aluminum, graphite, iron, copper, cement, glass, granite, and even steel. What you do have here that you need to memorize is the specific heat of water. Now you are expected to know this, so remember, memorize this. Okay, memorize this. And the unit, of course, for this will be joules, grams, degrees Celsius. Okay, so that'll be your unit for the specific heat of water. Now just take a moment and look at it. Notice how the specific heat of water is extremely high. In fact, it's one of the highest on this table. If you look at it, look at the specific heat of aluminum, and then look at the specific heat of gold versus granite versus wood. All the specific heats are very low, but water tends to have a very high specific heat. That means it takes a lot more energy to increase the temperature of 1 gram of water by 1 degree Celsius. So it takes more energy, where it really doesn't take that much energy to increase the temperature of 1 gram of gold by 1 degree Celsius. So good thing our oceans are made up of water and not of any other substance right here. These are other organic substances. If that was the case, our oceans would have evaporated a long time ago with the heat of the sun each time that's there. So based on this, you can specific heat can really come in handy. Now using this information, let's do some practice specific heat problems, and then we'll go into calorimetry problems. Now remember that the unit for specific heat is C. So in case I didn't put it on here last time, the unit for specific heat is actually C, and it's a lowercase c. Okay, So this actually is a specific heat for the specific heat symbol. The M stands for mass. The Q, you know, stands for heat. And of course, this change in T means change in temperature, and that is your final temperature minus your initial. With this being said, we say that Q equals MCAT because it literally looks like MCAT, so MCAT, okay? So let's get started. One of the first questions we have is, how much heat is required to warm 122 grams of water by 23 degrees Celsius? So in this problem, you're trying to solve for heat. That's what you want. So you're going to end up solving for Q in this equation, okay? So I'm going to write this equation here again, but it's Q is equal to MC change in T, okay? So you're going to solve for this Q equation. You're given mass as well as the change in temperature, which is 23 degrees. You're not given specific heat, but it's water. You're given the name of the substance, so you know the specific heat of water is 4.184 joules divided by grams degrees Celsius. So we've got it right here. This is our equation. We don't need to manipulate it because we've got Q that we are solving for. So you simply, in this case, just plug in your numbers. So it's 122 degrees times your specific heat of 4.184, and then times the degrees Celsius, your 23 degrees Celsius. Now notice that the grams will cancel out with the grams in your specific heat because this is in the numerator and this is in the denominator. Your degrees Celsius, which is in the numerator, will cancel out with the degrees Celsius in your denominator. And then you are just left with joules, which is what you want because remember, heat is another form of energy which is measured in joules. So in this case, when you plug this into your calculator, you get about 11,740.304 joules. Now that there are three significant figures, this is 1, 2, 3, 1, 2, 3 significant figures. So what you're going to do is you're going to round this up to three significant figures. So your answer is 11,700 joules. Okay, now I want you to pause this and then I'll be right back and I'll show you the answers to all the other problems and maybe go over some of those problems with you. All right, you guys, so here's the second example. Solve it the exact same way and your answer should be about 4,520 joules. And then you've got your third problem, which is a little different because the third problem you're actually solving for a specific heat of a substance. The substance that they give you is iron. But if you're solving for specific heat, remember that since you're solving for that, you're going to solve for C, and your answer should come out to be 0.449 joules divided by grams degrees Celsius. Remember, you guys, that right here in this equation, this is a little different because if you look at number 3, it says a sample of iron with a mass of 10 grams is cooled from 50.4 degrees Celsius to 25.0 degrees Celsius. If the total heat of the energy is 114 joules, what is the specific heat of the iron? Well, notice that the temperature right here, you go from 50 all the way to 25. So clearly your temperature has decreased. So what's happened to the heat there? Well, that means that the heat has actually been released or the heat has been lost. So that tells you that your Q value here is going to be a negative sign. So don't forget to put this negative sign in front of your Q. And when you do, right here, your temperatures are going to be also a negative value. So negative divided by negative will then give you a positive Q, positive specific heat value. Okay? So, and this is 3 significant figures, so your answer is 3 significant figures also. The next one, number 4, is a little different because you are trying to find the initial temperature of a substance. So, let's see. Let's start off over here where you can see this. So, if 335 grams of water at 65 degrees Celsius is lost at 9,750 joules, what is its initial temperature? So first of all, you're given mass, You know what substance you're working with, so you know the specific heat. You know that it's at 65 degrees Celsius, but then the heat is lost. Once again, you guys, that means that your heat or your Q value will be negative. So it's a negative 9,750 joules. And then you are trying to find the initial temperature. So this is the equation that you're actually using right here. You can solve for TI, or what you can do is just keep this as a bulk and have this as your equation that you actually have. So TF minus TI equals negative Q divided by mass times specific heat. So you can plug in your numbers, the values that you're given. Don't forget that you have that negative heat value, and because of this, you should get a negative degrees Celsius temperature. Now you can then plug in, because you have 65 degrees Celsius, well, that's your final temperature. So if you look at this equation, this negative 6.956 degrees Celsius is equal to 65 minus your initial temperature. We'll subtract 65 on both sides, and when you do, you get a negative 71.96. Keep in mind, you guys, that you are working with two significant figures. So if you are working with two significant figures, notice that the numbers here, the reason why it's two significant figures is because of the 65, which is the only number with the least number of significant figures, or the lowest number, so that's 65. So your answer will have up to two significant figures. Well, your temperature is a negative sign, but this is a negative initial temperature. So you can literally cross out the negative signs and have that your initial temperature is equal to 72 degrees Celsius. Okay? Example number 5 is exactly the same, you guys, as number 3. The only difference is that in here it does ask you to identify the substance. So if you go back to your chart, right here, you have specific heat is 0.449. You go back to this chart, the only substance that's even close to that number is iron right here, 0.450. I guess you can say steel, but that would give you more information. So you're just going to have to round it up to 0.450, which is what iron is. And then the last problem we have is a calorimetry problem. It's, remember Loki, law of conservation of energy? Well, Loki, you guys, the law of conservation of energy says that energy in a system is constant. It is conserved. So your energy is not going to leave the system. So let's read the problem first. It says here that 200 grams of lead, and it gives you the specific heat of lead at 170 degrees Celsius, is dropped into 100 grams of water at 40 degrees Celsius. What is the final temperature? Okay, so first of all, let's look at this. Let's look at exactly what's happening in here. You have a beaker, okay, of course it's closed and everything, but you have a hot cube, a hot piece of lead, and here's my lead. This lead, it has been heated to 170 degrees Celsius. Now you take this lead right here, heat it up, and then when you drop it in this water, remember that this water has an initial temperature, and I'm going to draw it up to here, water sign. So this water in here has a temperature of 40 degrees Celsius. But once you drop this hot piece of lead in here, now this temperature, the lead is going to start cooling off, but the water that the lead is in is going to start warming up. So eventually what's going to happen is that both the piece of lead here and the water will reach a equilibrium temperature. Well, the temperatures will be equal. The lead, which is at 170 degrees, will cool off, and the water, which is initially at 40 degrees Celsius, will actually warm up, where they both will meet an equal temperature. And that equal temperature is what we call the final temperature. the final temperature will be shared by both the piece of lead and the water itself. So when we go back to this problem and looking at this problem right here, you've got your equation and you've got your equation set up to 0 because of low-key law of conservation of energy, where within the system the energy is constant, it is conserved. Because it's constant, we're going to say that it's 0. And you've got the mass of lead, the specific heat of lead, the change in temperature, the final temperature minus the initial temperature of the lead, plus the mass of the water, the specific heat of the water, the final temperature. Now notice I haven't identified this final temperature because this final temperature you will both the water and the lead will share with one another. It's going to be the exact same temperature because that's where they reach equilibrium. And then of course minus the initial temperature of the water set up to 0. So you can start plugging in your numbers, the 200 grams times the specific heat of water, you don't know what the final temperature is, minus 170 degrees Celsius for the lead, plus 100 grams of water, the specific heat of water, you don't know what the final temperature is, but you do know what the initial temperature of water is, equal to 0. Now you're going to put your multiply through, so you're going to multiply this and you should get about 200 times the specific heat times TF, so you should get about 25.4 final temperature. And you're going to once again multiply the mass and the specific heat, but this time by 170 degrees, and you should get, since this is a minus 4,318. And then you're going to do the same thing, 100 grams times the specific heat of water, which is 418.4 times final temperature. And then, of course, take these two numbers and multiply it by 40 to give you negative 16,736, which is equal to 0. So you're going to carry the 0 through. Now you're going to combine like numbers, so you're going to combine all your any TF variables that you have, you're going to combine and have it equal to the other side to the other remaining numbers. And you're going to solve for TF, or your final temperature. Because this is two significant figures, because of the 170, the 200 right here happens to be 1, 2, 3, 4 significant figures. This is also more than that, not any less than that. This happens to be 2 because this 0 does not count. There isn't a decimal after it. And this is more than 2, and this is obviously more than 2 also. So you're looking at the least number significant figures in your question, and that is 2, thanks to the 170. So your final answer is going to be 47 degrees Celsius. Okay? I hope this helped you understand how to do energy unit conversions, understand what calorimetry is, and then do specific heat in a calorimetry problem. Once again, this is Ms. McBride speaking, and hopefully this helped you.